Hi, and welcome to Tellurium Tutorials. In this video, I will show you how to make a model of a Lorenz attractor using Tellurium. The Lorenz model is the basic model for thermal convection defined by three differential equations. Here, we're going to define our model in terms of these three equations. The rate laws defined here are defined by the three differential equations of the Lorenz attractor, and these initial constants will provide a chaotic oscillator. Now let's set some initial values. These initial constants are very specific because depending where the Lorenz attractor model starts, it will have different behaviors. I will show you in a moment how if you change the initial behaviors, you won't necessarily have a chaotic oscillation. Okay, now we're going to go m equals r dot simulate. We're going to go from 0 to time 40 with 3,000 points. We're going to say we want x, y, and z. Then, for the time being, we're only going to plot two of these to get a 2D graph. So all we're going to do is plt dot plot m. We'll do x and y. Let's go. As our label. Now when I run this, we can see that we have this very interesting butterfly graph of two of the values from this model plotted against each other. We can see that it chaotically oscillates between these two lobes of the butterfly as time continues. Next, let's turn this into a 3D graph so we can plot all three values against each other. We're going to have to go fig we'll change the fig size. And then this needs to become 3D, so we have to use the AX and add our other value. Then we go ax.legend and plt.show. Now when I run this, ax, oh, I know why, I didn't define what ax is. Ax equals fig.gca, and that says get current axes. If there aren't current axes, it'll create them. We want projection equals let's clean this up a bit. There we go. Now when I run this, oh, well, because I plotted x twice. That would be a good reason. Now when I run this, we see I have this very beautiful chaotic oscillator between these two lobes and all three values. So, maybe you want to know what happens if we change these initial constants. Let's get it so it's a non-chaotic oscillator. We see that we have a non-chaotic oscillator. It still oscillates between these two lobes. However, it's no longer this chaotic nature that we see in the graph above. Let's do one more. Let's change it so it's a single oscillation. Okay, now when I run this, we can see that it oscillates on the same path back and forth infinitely. Let's bring it back to our chaotic oscillator. I run it one last time. You can see that we're back to our Lorenz attractor plot. And all in all, it's a very cool plot. Thank you for watching. Now you know how to plot a Lorenz model using Tellurium.